Aloha, Kako. Hello, everybody, and welcome to Cosmic Questions with Spaceman Steve. If we haven't met before, my name is Steve, and I'm an astronomer at the James Clerk Maxwell telescope right here in Hawaii. And today is a very special day all around the world and on the Hawaiian Islands because it is Pōwehi Day. That's right, on this day, 1 year ago, April 10th, 2019, the very first image of a real-life black hole was released for the public to gaze upon in awe. This, right here, is Pōwehi. Pōwehi is the name given to the supermassive black hole that resides at the center of the Galaxy M87. This name was bestowed upon this cosmic wonder by the grandfather of the Hawaiian revitalization movement, the great Uncle Larry Kimura. Pōwehi is a name that comes from the Kumalipo, which is a Hawaiian creation chant, and it means embellished, dark source of unending creation. Chills. So, today, what is a black hole? Why do we care about them? How did this image come to be? And what's next? If we're going to understand black holes, we first need a crash course in gravity. In the 1600s, there was a man by the name of Sir Isaac Newton who developed the first mathematical theory of gravity. This brooding hunk, right here, thought that gravity was the attractive force between two objects that have mass. He was the whole apple falling on the head guy, but that probably didn't actually happen. Newton's theory is part of what we now call Newtonian physics, and it actually held up really well for a give or take 400 years. And the cool thing is, not only did this theory work on the Earth, it seemed to work everywhere. For the first time, humans could accurately calculate the orbit of planets around the Sun, and the Moon around the Earth. Physics! It happens everywhere! So, everybody was really happy until Einstein came along in the 20th century and said, "Newton, love you buddy, but you're a bit wrong." Einstein actually developed a theory that said that gravity is the warping and bending of space and consequently time itself. Space and time. Space-time! This actually fit better than Newton's theories. And it's held through the test of time. Einstein's theory of general relativity has been hailed a triumph through every experimental test that we have ever thrown at it. It's kind of why he's famous. Oh, also because he discovered the speed limit of the universe, which is the speed that nothing and no one can travel faster than. The speed of light. Yeah, really smart guy. Kind of an Einstein, you could say. We can think about the strength of the gravitational pull of an object by the amount of work that you have to do to escape that object. For stronger gravitational pulls, you have to travel faster and faster to try to escape. For instance, on the Earth, if you got tired of the planet and you wanted to start traveling through the vast expanses of space, all you would have to do is achieve a velocity of 11.2 kilometers per second. That way. If you did this, you could actually escape the Earth's gravitational pull because of your very fast velocity. And there's a name for this. It's called the escape velocity. But imagine with me, if you will, an object that is so small, so massive, so dense, that not even light can travel fast enough to escape its gravitational pull. This is a black hole. Now you can think of this idea kind of like a waterfall. If you were swimming at the top of a waterfall, don't. The closer that you got to a drop-off, you would have to swim harder and faster to try to get away. That is, until you actually go over the drop-off, and then no amount of CrossFit is going to save you, you cannot swim up vertically. This point of no return around a black hole is called the event horizon. It's the place where not even light can travel fast enough to escape the ravenous monster that lives within. Anyway, weird stuff happens around black holes. Light bends in a trajectory around the object. Time physically slows down when compared to reference points farther from the black hole. Weird stuff that Einstein's theory predicted 100 years ago. And here is the crux of the matter. We cannot recreate on the Earth the exotic physics and heavy gravitational pulls of black holes in laboratories here. So we have to use black holes out there in the universe as laboratories to test for the most fundamental nature of our universe, to understand whether Einstein's theory truly is correct about black holes and the physical observations match what the math said 100 years ago and has held so far today. So for years, we've known that black holes exist, but indirectly. For instance, over the course of decades, we've measured stars orbiting around the supermassive black hole that lives at the center of our own galaxy, the Milky Way. This black hole is called Sagittarius A star. We have also witnessed giant relativistic shooting jets from active galaxies far, far away in the distant universe, where material is launched from a place just outside the black hole called the accretion disk. And in 2016, you may remember the amazing news about the gravitational waves that were detected, ostensibly by two black holes colliding together and producing a signal that for the very first time we could measure here on the planet Earth. But all these years have gone by, and though we've had indirect evidence, we have never had a real picture of a black hole for the smoking gun that Einstein's theory is correct and black holes really should exist. You could say that we've always had fingerprints, but never the mugshot that we really needed. And if you're wondering why this is the case, it's because though the shadow of a black hole is physically very large, even larger than our own solar system, they are very, very far away. So from our perspective, big things far away look tiny. It's kind of like the old joke about the old man sitting in the park wondering why frisbees get bigger as they get closer. And then it hit him. The thing is, we've needed a telescope that is capable of unprecedented resolution. The same resolution, in fact, to see a single orange on the surface of the moon. Now, the resolution of a telescope is actually proportional to its size, which is a fancy way of saying the bigger the telescope you have, the better the resolution. And when we looked at candidate targets for what black holes we could potentially observe, it turns out to really see a black hole, to get a sharp image of the black hole itself, we would need a telescope the size of the entire planet Earth. Now, obviously, we can't build a telescope that is the size of the planet Earth because that's too expensive. So what did we do? We harnessed the power of physics, and we used a technique called interferometry. Essentially, it is possible to record the light received at different telescopes at different sites all over the world, as if they are all just some pieces of one gigantic mirror. And then we can very precisely line up these observations and focus them together using powerful computers after the observations are actually taken. The resulting image will have the same resolution as if it was taken by a single telescope the size of the distance between the sites on Earth. Sounds hard, right? Well, the guy who invented it, Sir Martin Ryle, won a Nobel Prize for it, so don't beat yourself up if you didn't come up with it first. The Event Horizon Telescope, led by Dr. Shep Dolman, went around the world connecting telescopes together to form a big synthetic dish, all the way out here in Hawaii, down in Chile, Arizona, the South Pole, France, all over the world to create a synthetic dish the size of the globe. The James Clerk Maxwell Telescope and the Smithsonian Submillimetre Array, which are out here in Hawaii, were a crucial point in this big Event Horizon Telescope system. That's because we extended the distance all the way out into the middle of the Pacific Ocean, creating a bigger mirror so we can get better resolution. Yay! Hawaii! Well, folks, there was so much data taken over a few days that it was actually impossible to send over the internet. Copies of the data were made, and it was physically flown to two different sites, one in Massachusetts and one in Germany. Now, 4 independent teams worked tirelessly to reconstruct the images taken by each telescope together to produce one final image of the black hole. Additionally, several independent teams used supercomputers to theoretically model what the observations should look like based on Einstein's equations that were written 100 years prior. Well, in the end, all 4 imaging teams produced results that were statistically identical. We now know that Pōwehi is 6.5 billion, with a B, times the mass of our own sun, and that our entire solar system can fit within its shadow. Finally, we got the mugshot that we were always looking for. The first direct evidence, the first direct photograph that black holes truly exist and Einstein's equations still hold true today. The Event Horizon Telescope is far from finished though. Just this week, a press release came out that the telescope imaged the launch site of these relativistic jets that are generated in the exotic environment from just outside of a black hole called 3C279. Just kind of rolls off the tongue, doesn't it? This is the first time that an observation like this has ever been made, and it's already showing us unexpected things, like a twisting of the jet. And what's really cool is that from day to day, the picture changes, so we can see the real-time variability of the physics just outside of a supermassive black hole. In the future, the team also plans to release images of the supermassive black hole that lives in our galaxy, the Milky Way. And Shep Dolman has also indicated that in the next decade, he expects real videos of swirling material around black holes and falling into the black hole to also be available as technology improves. This is going to blow people's minds. So, it's just the beginning. And here in Hawaii, the James Clerk Maxwell Telescope and the Smithsonian Submillimetre Array provide an absolutely critical role in furthering the study of black holes and understanding the fundamental nature of our universe itself. Mahalo nui, everybody. Thank you so much for watching. A hui ho. Until next time, I'm Spaceman Steve.